So this is more of a vocabulary video here than anything else. You are expected to know the different types of discontinuities, and there are four basic types, one of which has two subtypes. We have removable, which would be a hole or removed point. We have a jump. We have an infinite discontinuity, which you already know under a different name, vertical asymptote, and we have oscillating. I wanted to kind of show an example of what each graph looks like, and if they were to ask you why there's a discontinuity, what part of our discontinuity at a point causes the problem? So with this, holes you've seen before. So this would be an example of if we have a function where we can simplify, where we set the denominator equal to 0, but when we simplify it, it would cancel out. So in this case, x equals 2 is not in the domain of this function because it would give me 0 in the denominator. But when I simplify the function, the x minus 2 cancels. That leaves us with a hole. Now, if I'm asked, how do you know it's discontinuous there? Well, I have three options. Either the function does not exist at 2, the two-sided limit does not exist at 2, or the two-sided limit and the function don't have the same value at 2. In this case, for a hole, f of 2 does not exist. And that would be why it is discontinuous there. A moved point is like a hole, but it's like we took the point out of that hole and moved it up or down to a different place. A hole, we just took this point out and threw it away. Here, we took the point out and moved it. This is a discontinuity, not because the function doesn't exist, because the function does exist at 2. It's right here. The two-sided limit does still exist, but the two-sided limit and the function do not have the same value at 2. In this case, my function value, f of 2, is 1. The two-sided limit is 4. Those aren't the same, so it is discontinuous. Jumps are a very common discontinuity we see with piecewise functions. With a piecewise function, we kind of always want to check for jumps because they're so common in piecewise. Here I can see that there's a discontinuity at 2. The reason that there's a discontinuity for a jump is because the two-sided limit doesn't exist, because the left-hand limit and the right-hand limit won't be equal. So the two-sided limit not existing, I can even go further and say it's because the left-hand and right-hand limits aren't the same. For vertical asymptotes, we've kind of already talked about these. So they're most common in rational functions where we set the denominator equal to 0 and it does not cancel. So here I can see I have a vertical asymptote at x equals 2. With vertical asymptotes, I have multiple reasons to give for the discontinuity. For one of them, I could just say, well, the function value doesn't exist at 2, because if I try to plug 2 in, I can't actually find that. Or I could say the two-sided limit doesn't exist. In this case, the right-hand limit is positive infinity, the left-hand limit is negative infinity. Those don't match, the two-sided limit doesn't exist. But even if they were both positive infinity, and the two-sided limit, I could say, equals infinity, all that means is that the two-sided limit does not equal a real number, so it still doesn't exist. And then we have oscillations, or oscillating discontinuities. These are weird. I have never seen one of these on the AP exam. That doesn't mean they haven't done it. I've just never seen it. They're incredibly rare within introductory calculus like the AP course is. They do show up in electrical engineering when you're working with circuit design and dealing with alternating current. What's happening in an oscillating is, here I can see, well, I can't plug in 0 because it would make my denominator 0, but whereas 1 over x would be approaching infinity or negative infinity, when I take the sign of that, I get weird behavior where my function is trying to bounce back and forth between positive and negative 1 at the same time, without actually trying to connect them. It's trying to say, oh, it's +1, and immediately tries to jump down to -1 and back to +1 and down to -1 without any connection in between. Again, like with vertical asymptotes, we can give different reasons. I can just say, well, in this case, there's a discontinuity at x equals 0 because I can't plug 0 in and get a real number. F of 0 does not exist. We do also have an issue with a two-sided limit not existing, but that's a harder one for you to be able to show happening. It's just easier to say f of 0 doesn't exist in this case. And so here in this graph, I have different discontinuities. So at x equals -7, there's an infinite or discontinuity or a vertical asymptote. And I can see, whoops, from this that if I'm asked for the reason it's discontinuous, I can say, well, f of -7 doesn't exist. Or I could say the two-sided limit is -infinity, which is not a real number and doesn't exist. At x equals 5, there's a jump discontinuity. And if I'm asked for the reason, I can say, well, the left-hand limit as x approaches 5 from the left for this function f of x is equal to 4. The right-hand limit as x is approaching 5 from the right for this function f of x is 6. So the left-hand, or so the two-sided limit as x approaches 5 for f of x does not exist since the left and right-hand limits aren't the same. At x equals 13, I can see that there is a moved point. If I also put removable for the type, that is acceptable. I can see, in terms of reason, I can see that f of 13 is equal to 4, whereas the two-sided limit as x approaches 13 from the left and the right for the function is equal to 3. And I can now see that f of 13 does not equal the two-sided limit as x approaches 13 for the function. At 18, there's a hole. And again, if I put removable, that is okay. And in this case, f of 18 does not exist, would be my reason. So now that we've kind of talked about the types of discontinuities and showing discontinuity at a point, we can come back and actually give a better definition for continuous functions. Continuous functions are functions that are continuous at every point in their domains. So if there's a single discontinuity anywhere for that function, it is a discontinuous function. This actually simplifies things for us because it's easier to find discontinuities than to find all of the continuities. So that's kind of summing that part up.